Fiber optic cabling is going to represent data not as electrical pulses, but as pulses of light. The absence or the presence of light is going to indicate if we're sending a binary 0 or a binary 1. And since we're using light to send data instead of electricity, this completely gets rid of the issue of electromagnetic interference, or EMI. We're immune from that by using fiber optic cabling. And fiber optic cabling tends to have a longer range. It can reach further distances than unshielded twisted pair. For example, let's say that we have a campus environment and we're trying to connect buildings around a college or a business campus. If the distance between the buildings exceeds 100 meters, that might be a great fit to use fiber optic cabling. When you go out to purchase fiber optic cabling and equipment, however, you should realize there are two primary types of fiber optic cabling. We have different types of connectors that we might see on a fiber optic cable. For example, there's an ST connector, or a straight tip connector, an SC connector, or a standard connector, an LC, a lucet connector, or an MTRJ, media termination recommended jack connector. The MTRJ is kind of unique in that within the single fairly small connector, we have two fiber optic strands. The connector you see pictured on screen is an SC, a standard connector, but we said there were two types of fiber optic cables. We have multi-mode fiber, abbreviated MMF, and we have single mode fiber, abbreviated SMF. To help us start to understand the distinction between multi-mode fiber and single-mode fiber, consider what you may have seen at a restaurant. Let's say that you had a glass of water and you had a straw in your glass of water. You might have noticed a phenomenon something like this. When you insert a straw or a pencil or something into a glass of water, have you ever noticed that the straw or the pencil, those objects don't seem to line up above the water line and below the water line? What's happening is something called refraction. Specifically, air and water have a different index of refraction, a different refractive index, meaning that light travels at a slightly different speed in water and in air, causing the light to bend. That's what's happening with a fiber optic cable. If we were to zoom in on a strand of fiber optic cabling, it would look something like this. And by the way, we have two strands typically when we're connecting a piece of equipment. One strand is for transmission and one strand is for reception. Here on screen though, we're just zooming in on a single strand of fiber optic cabling, and you'll notice that it's not a single piece of glass. You'll notice that we have an inner core, and outside of the core we're surrounded by an outer cladding. We have a core, let's label these. We've got the core, and we've got the cladding. And the index of refraction is so different between the core and the cladding, just like the glass of water would bend the light a little bit. The indices of refraction are so different between these different pieces of glass that the light literally bends back on itself. It cannot escape the core. It's going to work something like this. We have a beam of light, like a laser or an LED coming in. It hits the edge of the core, that barrier between the core and the cladding, and again the index of refraction is so different that it's going to bounce off, and it bounces off the other side, back and forth, back and forth. It bounces its way down the core of the fiber optic cable. And with multi-mode fiber, the core has a diameter that's large enough to allow light to enter the core at different angles. I showed the light entering at one angle. What if we entered at a steeper angle? Like this. If I entered at a steeper angle, there's going to be more bouncing involved, isn't there? Back and forth, back and forth, back and forth. Do you see what's happening? It's taking us longer to get out of the core because we're bouncing back and forth more frequently. Over a long distance, such as greater than 2 kilometers, we could have an issue with this. If one bit comes in at a steep angle, like the green line on screen, and the next bit comes in at a less steep angle, like the red line on screen, it's possible that the bits would get out of order. The first bit came in first, but it bounced back and forth, back and forth, back and forth much more than the next bit did. It could actually fall behind, The name for this is called multi-mode delay distortion. A mode is a path over which our light is going to propagate. Light is going to travel over a particular path. That's a mode. I've drawn 2 modes on screen, but we could have lots of modes with this particular fiber optic cable because the diameter is large enough to support multiple modes to be transmitted. It's less expensive to manufacture a multi-mode cable. The way it's manufactured is there are different levels of dopants put in the core and the cladding to give those 2 different types of glass a different index of refraction. But if we have higher manufacturing tolerances, and we can have a smaller diameter, if the core is smaller, it could be so small that we would only have room for 1 mode. In that case, our mode of propagation could only go down the middle of the core. The diameter is not large enough to allow light to enter at another angle. That's not going to work. A larger angle of incidence, as it's called, is not going to be supported. Because the diameter is so small, we only have 1 mode, only 1 path that the light can take. That's called single mode. And because single mode eliminates the issue of multi-mode delay distortion, because we don't have multi-modes, this means that we can achieve much greater distances, maybe 40 kilometers as an example, with single mode fiber as opposed to multi-mode fiber. But to sum up, fiber optics, it's going to represent data as the presence or the absence of light. Therefore, it is immune from electromagnetic interference. It's often used when the distance requirement for a connection is greater than that supported by unshielded twisted pair cabling. It supports high data rates, and we have 2 types. Multi-mode, which is less expensive than single mode. And the reason multi-mode is less expensive is it has a larger diameter for the core, which could allow multiple modes, multiple paths of light to go into the core, which could result in multi-mode delay distortion. That issue is eliminated with single mode fiber.